In this presentation, I'm going to be looking at this part, derive the formula for the EMF induced in a straight conductor moving in a magnetic field. We will need to call on information and knowledge that we already have about the electric field strength and about a charge moving through a magnetic field. So imagine we've got a wire like that with length L, and it is moving with a certain velocity downwards like that through a magnetic field, and the magnetic field is going into the board. And imagine this magnetic field is uniform through the whole area. This wire is going through this magnetic field, which is going through this whole area. Now, in this wire are electrons, and they will therefore be moving through the magnetic field with a certain velocity. Now, the formula that we have for this is F is equal to QVB sine of theta, where Q is the charge, and in this case it's an electron, so it's got the charge on an electron, 1.6 times 10 to the negative 19 coulombs, times the velocity times the strength of the magnetic field. And because the magnetic field is at 90 degrees to the direction, to the velocity, this theta is 90 degrees, and therefore the sine of theta is equal to 1. So we have got that. Now, this force will actually set up an electric field. It will actually cause the electrons to move. So if we use our right-hand rule, we can see that because it is going downwards, we will have our thumb in the direction of the current, which will be in the opposite direction. The fingers will go in the direction of the magnetic field, so the force on a positive charge would be to the left, and therefore on an electron would be to the right. So it would have to actually have these electrons all moving over. So if this was a piece of wire, we'd actually get a negative charge on this side and a correspondingly positive charge set up on this side, and it would set up an electric field. Now we know that the formula for this is that the electric field strength is given by the force divided by the charge. So we therefore have the force is equal to the electric field strength times Q, but Q, because we're looking at electrons, is E. So I can replace this force by this EE, and I get the EE, electric field, and the charge on electron is equal to EVB. And what happens is my small e's cancel, and I've got my electric field strength is equal to VB. Now, we can now consider that we have got this electric field strength, and this is similar to parallel plates. Now I'm going to go over here. I'm going to start discussing in this section over here. We have a formula for that. The EMF, or I'm going to put it in brackets, the V, for parallel plates, and we can actually view this wire as like parallel plates, is equal to the electric field strength is equal to V over D, and we are going to, instead of writing V, we are going to use this symbol. This is for the EMF. So we're going to have that your electric field is equal to V, which I'm going to use that, the curly E, for the EMF, and the D is your length, so it's over length. So I'm going to replace that into this formula. So I'm going to get E over L is equal to VB, and I can cross multiply and rearrange. Therefore I'm going to get my EMF is equal to BVL. And if I have got multiple turns in multiple turns, I will come and write over here, I will have that E is equal to NBVL. And this is the formula for the electric field, electromotive force, the EMF, that is set up when you are moving a wire of this length with a certain velocity V through a magnetic field of strength B, and if this is the number of turns, the EMF is given by this value.